Welcome back to the third chapter 11 video. We're going to look at hydration and hydroboration. So we have 11.9 is the addition of water or hydration. And same idea, we're going to go through some mechanisms and then we'll kind of go through it in parts. Okay, so essentially you can take an alkyne, it's not a Z, that's an alkyne, kind of dragged, and you're going to add H2O excess, let's say, H2SO4 catalytic, just like we did with an alkene. Okay. And we also need HgSO4. Okay. Now, technically speaking, this is only for a terminal. Okay. We're just going to put in mercury sulfate each time, okay? And it's also a catalyst, okay? We're not going to worry about what that does. Probably is sort of helping bind to the alkyne a little bit to get initial protonation, but we're not going to worry about that, okay? But what we do see is ketone. I'm going to keep these bonds straight so we can see them. And what I really want you to notice when we draw it like this is that what do we have? H2O. Okay, that's where the water comes from. Because we got an extra double bond, we're going to see that water is added. Okay, we'll do arrow pushing in a minute. This is kind of a big picture. Water is added, and you get what's called an enol. Really important intermediate. We're going to talk about this a whole lot more in the course, both courses, Organic 1 and 2. But enols are a very special isomer. Keto-enol tautomerization is what it's called. Tautomerization is the back and forth. These are tautomers. Tautomers are just very special constitutional isomers. Tautomer. Constitutional isomers in equilibrium. Okay, so constitutional isomers that are in equilibrium are tautomers. Ketones and enols are, we're going to see how we can basically move this H over there onto the carbon. Okay, the carbon-oxygen bond is stronger than a carbon-carbon double bond, so the carbon-oxygen double bond is favored thermodynamically. Okay. So, again, just to show you an example, you can take a terminal, do the same reaction, H2O excess H2SO4 and HgSO4, both catalysts. And what can you get? Here you can get a methyl ketone. Same idea, H2O is added across the triple bond, so you get a methyl ketone. Okay, so let's walk through this mechanism. It's a lot of steps, and we have to break it up into 2 slides. We have the alkyne. We've got our conditions here. H2O excess, H2SO4 catalyst. Same things we've seen before. Now we've got this mercury sulfate. Again, you don't have to remember this condition per se, but I want you to recognize and not be thrown off by it. That says catalyst. These are the conditions necessary for an alkyne. What's going on with my pen? CH3 okay. All right. So what I'm going to say is this is a spectator mechanistically, HgSO4. Okay. What do we know happens when you mix water and sulfuric acid? You get H3O+. Okay, we've seen that before. Again, sulfuric acid is a very strong acid. It's going to give up its proton and form H3O+. Okay, I've said this before, but I want you to recognize this is still a good acid. Okay, this is the active acid. Just like an alkene or an alkyne will pick up an H from HCl or HBr, it's going to pick up this H from H3O+, giving what? An alkene, carbocation. Again, I don't love drawing these because there's debate about whether these form, but this really gives us a theme. Okay, draw out the sulfonate that's associated there. Again, this is a spectator. Okay, I've said that many times. The sulfonate is not doing anything. Sulfonate is not going to attack. It's not going to do anything else. We got lots and lots of water, right? We have excess water. Okay, so we're going to use that to attack the carbocation. Let's go ahead and break this up into two different slides. Okay, it's getting pretty busy. Doesn't look so different. Okay, sulfonate, again, that is not deprotonating. What do we have? We have a mixture of water, or we have we have plenty of water that we can use to deprotonate. This gives us the enol. Okay, we drew that before. I'm going to draw it on the next slide. I'm going to start with the enol. Okay. Draw it over here. Enol. Okay. So it's important to say this. You don't have to draw this, but you get a mixture of E and Z. Okay, the methyl and the OH could be switched. But you cannot stop here, okay? Because what do we have in here? We have H3O+. Sulfonate. The alkene is going to deprotonate to give you a carbocation, a very special carbocation. It's a CH3, sorry. So we protonated. Let's circle the H that was protonated. So this is a very stable carbocation. It's called an oxocarbenium. It's an oxygen stabilized carbocation. Stabilized by what? Resonance. We talked about this with the bromine. We introduced this very early in the course. We showed resonance forms for this. Again, we've got a sulfonate now. This, you can draw this once if you want, the sulfonate that is going to be with this. And then what happens? Not the sulfonate, but water. Will deprotonate, giving you the ketone. Regenerating, that's a 3. That's your final product. And then regenerating what? H3O+. Sulfonate. try to go over this whole mechanism in class, okay? But that's the idea. That's a hydration reaction. Hydration of an alkyne. Okay? I'm going to give you a take-home of a terminal. Now we have a choice. Ethynyl cyclohexane. We would name that if we were naming it. Ethynyl cyclohexane. Okay, I'll just give you some intermediates. Same conditions, H2O, excess, and everything else. Okay, H3O plus, etc. I'm just going to give you some intermediates. You can fill in the rest. Exact same mechanism, but I want you to see that you're going to get the more substituted alkene carbocation, right? Water is going to attack that, and eventually you're going to get to enol. Right, what's going to happen here? It's going to tautomerize. It's an acid-catalyzed tautomerization. Okay, we'll use that term throughout. More so in organic too, but we'll still use that. Right, you can go, you draw the resonance forms, etc. And what do you get here? You get a specific ketone. Now it's important, again, that you walk through this whole mechanism and work through it so that you get the right carbonyl. What we're going to see is for these kinds of things, we're going to get aldehydes with hydroboration. Here, so you get a ketone here. It's all mechanism. So work through that one, kind of a take-home mechanism. And then 11.10 is hydroboration, oxidation. We're going to see similar themes as we saw with hydroboration previously. Now let's look at, again, sort of an intro overview type of mechanism. R2BH, H2O2, sodium hydroxide. Gives what? It also gives a ketone when it's an internal olefin. We're going to see a really important difference when we have a terminal alkyne. We're going to get an aldehyde. That's really the major difference here. We're going to do hydroboration. Br, and then what happens? We're going to add H2O2, sodium hydroxide. We're going to get enol. And tautomerize. Okay, this is going to tautomerize. And that's that. So let's go through this mechanism. Let's make the point, though, first. Let's show a couple specific reactions. R2BH. So you can get ketones, but this one's really important. With a terminal alkyne with an H there, when you do hydroboration, you get the aldehyde. Really important. Okay, aldehyde. Let's go through the mechanism. Okay. What I want to do is walk you through the mechanism for the terminal. Okay. We're going to abbreviate some things on the tautomerization for this one because the really important thing is understanding the regioselectivity of the hydroboration. let's show this. It can line up two ways. What's going to happen? The more stabilized carbocation, the more partially positive, is going to line up with the partially negative hydrogen. Okay? So the alkene is going to attack the boron, empty p orbital. This BH bond is going to attack that carbon. That's the right way to draw those two arrows. What happens then is you get the CH3 and the H on the same carbon, and you get the BR2 and the H on the same carbon. So notice the H and the BR, right? There's the circled hydrogen, the BR2. That's the only regioisomer that you get. And then what happens? You have sodium the sodium salt of hydrogen peroxide is going to attack. You get to this. Hopefully this looks kind of familiar. You got now an alkenyl borate, we would call that. And this is going to do a 1-2 shift, right? It's going to shift from the 1 of boron to the 2 of oxygen. 1-2, what we would call alkenyl shift. The name doesn't matter. It's a 1-2 shift from boron to oxygen. Kicking out hydroxide. We make some allowance for this because, again, in multiple molecules, bulk properties here, that OH minus is going to associate with boron. We make some assumptions as the mechanisms get more complex. Right? If there is an OH minus, rapidly going to attack boron. Okay, you got a sodium there. What happens here? This is where we're going to kind of stop the mechanism, so to speak. We're going to abbreviate what happens here because instead of a OH bond, we have an OB bond. Okay? We can go through this in class. We can talk about it as much as you want. But the idea is, just like the OH, think of oxygen metal bonds or oxygen boron bonds as kind of like a larger version of a proton. Okay, it's not a perfect way to think about it, but you might add some acid to this to quench it. There's just things that you can do where you get, some reaction with some form of H+. Again, we just are abbreviating some things, but notice the oxygen carbon double bond that's forming next to this H. Okay, it's going to tautomerize in some way. Okay, I got to break some oxygen boron bonds and things like that. So we make some assumptions there. The really important thing is that we make aldehyde. Okay, so we need to be able to predict those products, work through the mechanism. You can make the same assumptions that I make. So do this one, take it home. We already gave you the products, but quiz yourself. You can pause the video, quiz yourself on the video. What's the product here? And what's the mechanism? Right? Here you can line up the hydrogen boron bond either way, it doesn't matter, because it's symmetrical. Okay, so work through that one. And then I want to finish with making the point here. You have a terminal alkyne. If we treat this with H2O excess, H2SO4 catalyst, this mercury sulfate catalyst, what do we get? We would get acetone in this case. We'd get a ketone. But treat this with hydroboration conditions. What do we get? We actually get the aldehyde. big difference. Aldehyde for hydroboration, ketone for hydration. Do another example here. These aromatics don't react because they're stabilized. Okay, so alkynes will react. Same conditions. You get a phenyl methyl ketone. Same conditions over here. You get an aldehyde. Okay, so very important difference. We saw the same thing with alcohols and alkenes, so there's parallels there. When you react alkenes with hydroboration, you get a very different product than when you react alkenes with hydration conditions. Okay, so that wraps up the third video, and we'll have one more Chapter 11 video.